At this very moment, thousands of airplanes are flying above your head, invisible from the ground, carrying millions of people through the sky inside metal machines weighing hundreds of tons. No wings flapping, no magic, just pure science, keeping them alive at 35,000 feet. And yet, most passengers have no idea what is actually happening outside those small windows. Humanity dreamed of flight for thousands of years, but gravity always won. Ancient inventors failed, early machines crashed, and many paid with their lives. Until 1903, when a fragile aircraft stayed airborne for just 12 seconds. That moment didn't change transportation, it changed civilization. From that failure grew the most advanced machines ever built. A modern airplane is not a vehicle, it is a flying system. Built from lightweight aluminum alloys and advanced composites, every structure is engineered to survive freezing temperatures, violent winds, and crushing pressure differences. One aircraft contains millions of components, each designed with zero margin for error. Flight is controlled by only four forces: gravity pulling down, lift pushing up, drag slowing motion, and thrust driving forward. Flying is not about defeating gravity. It's about balancing these forces so precisely that falling never begins. The wing is where flight truly happens. Its curved shape forces air to move faster above and slower below, creating a pressure difference strong enough to lift an entire aircraft. When lift exceeds gravity, the plane rises, not because it wants to fly, but because physics demands it. Jet engines do not pull airplanes forward. They throw air backward at extreme speed. Air is compressed, fuel is ignited, and hot gases explode out of the engine faster than the speed of sound. Newton's laws do the rest. Every kilometer traveled is paid for with controlled explosions. Takeoff is the most demanding phase of flight. As speed increases on the runway, flaps extend to generate extra lift. The nose rises, the angle changes, and suddenly the wheels stop supporting the aircraft. From that moment on, the plane survives only on airflow and engineering. Cruising altitude exists for a reason. At 35,000 feet, air resistance is lower, fuel efficiency is higher, and weather is calmer. Outside, temperatures drop below -50 degrees, and oxygen becomes unbreathable. Inside, the cabin is artificially pressurized to keep humans alive in an environment that would otherwise be fatal. Turbulence feels dangerous, but it is not. Aircraft are built to withstand forces far greater than any turbulence passengers experience. What feels violent inside the cabin is often insignificant to the structure itself. The danger comes from panic, not physics. Even when things go wrong, airplanes are designed to survive. They can fly with one engine. They can glide without power. Pilots train for failures they hope never to face. Aviation safety is built on redundancy, systems backing up systems, human decisions backed by machines. Fear of flying is not logical, it is neurological. The human brain evolved to fear height, loss of control, and unfamiliar motion. An aircraft combines all three, triggering ancient survival circuits. Your rational brain understands safety, but your emotional brain reacts faster. That fear response activates adrenaline, even when no danger exists. The body prepares for impact that will never happen. On the ground, humans believe they have control, even when they don't. In the air, control is visibly absent, even though safety is higher. Car accidents feel familiar. Plane accidents feel catastrophic. Media coverage amplifies rare aviation failures. A single plane crash receives more attention than thousands of road deaths. This creates a distorted perception of risk. The brain remembers dramatic images, not statistics. Pilots experience none of this fear because they understand the systems. Understanding replaces imagination. Automation does not reduce safety, it increases consistency. Autopilot systems fly more smoothly than humans in most conditions. Pilots monitor, cross-check, and intervene only when necessary. Modern cockpits are built around error prevention. Flight paths are planned hours before takeoff. Weather is analyzed continuously during the journey. Pilots reroute long before storms become dangerous. Aircraft do not get stuck in storms, they avoid them. When turbulence happens, it is usually clear air turbulence, invisible but harmless. It cannot be detected by radar, but it cannot damage aircraft. Pilots know where it is likely to occur and adjust altitude. Cabin noise increases anxiety, not danger. Engine sounds change as power settings adjust, not because something is wrong. Silence during flight is not a failure, it is efficiency. Landing feels aggressive because brakes are powerful by design. Reverse thrust looks dramatic but is fully controlled. Hard landings are often safer than soft ones in poor conditions. Every aviation accident triggers an international chain reaction where investigators from multiple countries collaborate to reconstruct the final seconds of flight. Failures become lessons, not repeated mistakes. Investigators do not search for one cause. This philosophy is known as the Swiss cheese model, where multiple safety layers exist, but accidents occur only when the holes in those layers line up perfectly. Once a failure pattern is identified, it is not fixed locally, it is corrected globally. This is why aviation improves even when accident numbers are already extremely low. Redundancy in aviation is not duplication for backup alone, it is engineered diversity. Aircraft use multiple computers written by separate teams to prevent identical software errors. Modern cockpits are designed around the concept of human-centered engineering, ensuring controls, alerts, and displays match how the human brain naturally processes information. Air traffic control operates as an invisible safety net. Even when pilots make no requests, controllers intervene proactively if patterns suggest future conflict. Weather forecasting for aviation is so advanced that airlines reroute flights hours in advance. What passengers feel as violent shaking is often a tiny fraction of the structural limits engineers plan for. Behind every smooth landing lies thousands of micro-decisions made by machines and humans working in perfect coordination. Flying today is safer than it was yesterday, and tomorrow will be safer still. Every flight is tracked from the moment it moves on the runway. Modern aircraft continuously transmit their position, speed, altitude, and direction through satellite-based systems. This allows airlines and air traffic controllers to see aircraft even over oceans where traditional radar cannot reach. Air traffic control is a global choreography. Thousands of aircraft share the same sky, yet collisions are prevented through layered systems. Radar, satellite tracking, collision avoidance computers, and human controllers working together. No single system is trusted alone. Inside the aircraft, computers constantly calculate the safest possible path. If turbulence, storms, or restricted airspace appear ahead, the flight path is adjusted automatically or with pilot approval. Passengers may feel slight turns, but those changes are deliberate and calculated. Turbulence feels dangerous, but it is rarely harmful to the aircraft. Airplanes are designed to flex, not resist. Wings bend to absorb energy rather than brake. Engineers design them to withstand forces far beyond anything encountered in normal flight. The sounds passengers hear, engine pitch changes, clicks, hums, and whirs, are normal operations. Landing gear deploying, flaps moving, fuel shifting, and pressure systems adjusting all produce noise. Silence, not sound, is what pilots would worry about. Cabin pressure is carefully managed. At cruising altitude, the outside air would make humans lose consciousness within seconds. Aircraft recreate breathable conditions inside, slowly adjusting pressure during climb and descent to protect the human body. Oxygen masks are designed for short-term survival, not comfort. They provide just enough oxygen to keep passengers conscious until the aircraft descends to a safe altitude. That descent begins immediately, even if passengers are unaware. Fire is treated as the most dangerous threat in aviation. Sensors detect smoke instantly, even before flames appear. Fire suppression systems activate automatically in cargo holds and engine compartments without pilot input. Pilots follow strict checklists because memory fails under stress. These checklists are written in blood. Every line exists because something went wrong in the past. Aviation learns by never forgetting its mistakes. Maintenance is relentless. Aircraft are inspected daily, weekly, monthly, and annually. Some inspections require dismantling entire sections of the plane. Airlines ground aircraft immediately if even a minor fault appears suspicious. Commercial aircraft engines are among the most tested machines ever built. Before approval, they are pushed beyond operational limits, struck by debris, exposed to extreme temperatures, and run continuously for thousands of hours. Fatigue is considered a risk equal to mechanical failure. Pilot duty hours are strictly regulated. If a pilot is too tired, the flight does not depart, no matter the cost or schedule pressure. Weather remains the one force aviation does not challenge directly. Flights avoid storms instead of fighting them. Delays, diversions, and cancellations exist not because aviation is weak, but because it respects physics. Even emergency landings are rehearsed before they ever happen. Pilots practice losing engines at takeoff, landing without flaps, and descending without cabin pressure, all inside simulators that recreate stress with precision. What passengers see as routine travel is actually the result of millions of invisible decisions by engineers, controllers, pilots, and systems, all working together so that nothing dramatic happens at all. Before every flight, pilots calculate performance using exact numbers: runway length, aircraft weight, temperature, wind direction, and altitude. A few degrees hotter or a few tons heavier can change whether a plane can safely take off. Fuel planning is mathematical, not guesswork. Aircraft never load just enough. Regulations require fuel for the full journey, alternate airports, holding time, and unexpected delays. Running out of fuel is one of the rarest failures in aviation. Airports are designed like funnels. Taxiways, runways, and gates follow strict layouts to prevent aircraft from ever crossing paths unsafely. Even ground movement is controlled by clearance, not pilot choice. At high altitude, the sky is divided into invisible highways. Aircraft fly at assigned levels, separated vertically and horizontally. This layered structure ensures that even if navigation fails, planes are never on a collision course. Modern aircraft can land themselves. Auto-land systems use radio signals from the runway to guide the plane during heavy fog or zero visibility. Pilots monitor, but computers perform the precision. Despite automation, pilots never stop flying mentally. Hands may be off the controls, but eyes track instruments constantly. Automation is a tool, not a replacement for human judgment. Communication is standardized globally. Pilots and controllers use precise phrases to avoid confusion. Every word has one meaning, and emotional language is removed completely. Even accents are accounted for. Aviation English limits vocabulary intentionally so that non-native speakers can communicate under pressure without misunderstanding. Aircraft materials are chosen for failure, not perfection. Parts are designed to crack visibly before breaking completely. This gives engineers warning long before danger appears. The cabin itself is a safety system. Seats are designed to absorb impact, floors are reinforced, and luggage compartments are built to contain heavy objects during sudden deceleration. Seat belts are not symbolic. During turbulence, they are the single most effective protection passengers have. Most in-flight injuries occur when belts are not fastened. Emergency slides are aircraft in themselves. They must inflate instantly, support dozens of people, and function even if the plane is tilted, broken, or partially submerged. Cabin crew are not servers. They are trained safety professionals. Their primary job is evacuation, fire response, and crowd control under panic. Human psychology is studied deeply in aviation. Designers assume people will freeze, panic, or follow others blindly, and systems are built to counter those instincts. Lighting inside the cabin changes deliberately. Dimming before landing prepares eyes for darkness in case of evacuation, increasing survival chances. Even the color of emergency equipment matters. Bright contrasts help passengers locate exits when smoke fills the cabin and visibility collapses. Blackouts are expected scenarios. That is why floor-level lighting exists, guiding passengers when normal vision fails. Every accident reshapes aviation. One failure triggers redesigns worldwide. Unlike most industries, aviation shares mistakes openly so they never happen twice. This is why modern crashes are rarely caused by a single failure. Multiple layers must break at once, something aviation systems are designed to prevent. What makes flying remarkable is not speed or height, but how much effort goes into making the extraordinary feel completely ordinary. When something goes wrong in aviation, the industry doesn't hide it. It studies it obsessively. Every accident reshapes future aircraft design. Most safety rules exist because someone, somewhere, once made a mistake, and the system learned from it. Pilots are not alone in the cockpit. Every major decision is cross-checked between two trained professionals. This system is called crew resource management, designed to eliminate ego and hierarchy during emergencies. Checklists exist because human memory fails under stress. Aviation never trusts memory alone. Every phase of flight, taxi, takeoff, climb, cruise, descent, landing, has its own checklist. Automation helps, but pilots never surrender full control. Automation assists, it does not replace judgment. When automation behaves unexpectedly, pilots are trained to disconnect it instantly. Modern aircraft constantly diagnose themselves. Faults are detected before pilots even notice them. Maintenance crews receive digital reports the moment an aircraft lands. Some parts are replaced not when broken, but when they reach a calculated lifespan. This prevents failure before it ever happens. Aircraft are grounded immediately if safety margins are questioned, no matter how expensive the delay. Weather forecasting is integrated directly into flight planning systems. Pilots can see storm movement hours ahead, not just what's outside the window. Fuel planning includes reserves for diversions, delays, and unexpected holding patterns. A flight never launches with just enough fuel. Runways are engineered to stop aircraft even during rejected takeoffs at full speed. Special materials beneath runways absorb energy if an aircraft overruns. Firefighters are positioned before every takeoff, not after an accident. Cabin crew are trained more in safety than service. Every evacuation drill is timed. Seconds matter. Passengers rarely notice, but cabin lighting, aisle width, and seat spacing are all safety decisions. Even seat cushions are designed to float if water evacuation sees place. Life vests are not optional accessories. They are calculated survival tools. Aircraft doors cannot be opened at altitude. Physics makes it impossible. Fear often comes from not understanding control, not from actual danger. What makes flying remarkable is not just the machine, but the relentless, invisible system that keeps it safe. Landing is controlled descent, not falling. Speed is reduced, lift is carefully managed, and the aircraft reconnects with the ground. Spoilers destroy lift, brakes absorb massive energy, and reverse thrust slows a machine that moments ago was crossing countries in minutes. One of the biggest fears people have is fuel. An aircraft burns thousands of liters, yet never runs close to empty. Flight planning begins hours before takeoff, calculating fuel for the route, alternate airports, holding time, weather delays, and unexpected emergencies. Every commercial flight carries extra fuel specifically for things that never happen, just in case they do. Jet fuel itself is engineered for safety. It is harder to ignite than petrol and requires very high temperatures to burn. This reduces the risk of explosions during turbulence, lightning strikes, or hard landings. Fire in aviation is treated as an enemy, and fuel design is one of the first defenses. Lightning strikes airplanes far more often than people realize, usually once per aircraft every year. Passengers rarely notice because the aircraft is built like a protective shell. Electricity flows over the outer skin and exits safely, never entering the cabin. This is the same principle used to protect sensitive scientific equipment. Bird strikes sound terrifying, but aviation plans for them. Engines are tested by firing frozen birds directly into them at high speed. If an engine fails, it must shut down safely without damaging the aircraft. Commercial airplanes are certified to continue flying even after losing an engine midair. Pilots are not just drivers, they are systems managers. Most of the time, the aircraft flies itself using autopilot. The pilot's real job begins when automation fails. That is why they train repeatedly in simulators for fires, engine loss, pressure failure, and worst-case scenarios they may never encounter in real life. Inside the cockpit, every sound matters. Warning tones are designed so pilots can recognize problems instantly without looking. Different alarms mean different threats. In emergencies, seconds matter, and confusion is eliminated through training, not instinct. When a pilot says Mayday 3 times, it signals immediate danger to life. Air traffic control then clears the sky, prioritizes landing, and activates emergency services. A less severe call, pan-pan, requests assistance without signaling imminent disaster. These phrases exist so no confusion ever delays help. Statistically, flying is the safest form of transportation humans have ever created. Fear exists not because flying is dangerous, but because we surrender control. In reality, every flight is the result of physics, engineering, discipline, and decades of learning from failure. An airplane does not fly because of luck. It flies because thousands of minds solved millions of problems, and because science allows no shortcuts. Every safe landing is proof that when physics is respected, even gravity can be negotiated. Turbulence feels dangerous, but it is not. Aircraft are tested to withstand forces far beyond anything experienced in real flights. What passengers feel is discomfort, not structural danger. Wings are meant to bend. During testing, engineers flex wings upward until they curve like bows. If wings did not flex, they would snap. Pilots rarely see turbulence coming visually. Instead, they rely on radar and reports from aircraft ahead, creating an invisible warning network in the sky. Storms are never flown through intentionally. Aircraft navigate around them, sometimes hundreds of kilometers off course, prioritizing safety over speed. Ice is one of aviation's greatest enemies. That's why aircraft wings are heated internally, melting ice before it can form. Even if ice builds up, planes are certified to continue flying safely until landing. Redundancy exists even for worst-case weather. Bird strikes are expected, not feared. Engines are tested by firing frozen birds into them at high speed. The engine must survive or shut down safely. A jet can fly and land safely with just one engine. This is not a backup plan. It is a core design requirement. In fact, most engines are powerful enough that a plane could take off on one engine if regulations allowed it. Fuel tanks are placed inside wings for a reason. Wings absorb impact better than the fuselage, reducing fire risk. Static electricity builds up constantly while flying. Small sparks often discharge harmlessly from wing tips, invisible and normal. Lightning strikes aircraft more often than people realize. The electricity passes around the cabin, not through it. Passengers are protected by physics. Windows are not weak points. Each window has multiple layers, each capable of holding pressure independently. The small hole in aircraft windows is intentional. It controls pressure between layers, preventing cracking. Oxygen masks do not feed oxygen forever. They give just enough time for pilots to descend to breathable altitude. Cabin air is replaced every few minutes. Aircraft ventilation systems exchange air faster than most buildings. This air is filtered through HEPA systems, similar to hospital-grade filtration. Fire is the most serious threat in flight. That's why smoke detectors exist even inside cargo holds. Cargo fires are suppressed automatically. Pilots may never even know one occurred. Pilots train in simulators more than real aircraft. Simulators recreate failures too dangerous to practice in the air. Every emergency procedure is memorized, practiced, and repeated until it becomes reflex. Air traffic controllers track aircraft not just on screens, but in 3 dimensions of space and time. Controllers plan minutes ahead, preventing conflicts before they exist. Loss of communication does not mean loss of control. Aircraft continue flying predictable routes automatically. Even total electrical failure has backups. Mechanical systems still allow pilots to control the aircraft. Every system has a backup. Most backups have backups of their own. Aviation safety is built on one philosophy: assume something will fail and be ready when it does.